All right, let's jump right in. We're surrounded by this invisible world, a constant, silent storm of data flying through the air, connecting our phones, our laptops, our smart speakers, everything. And for the most part, it just works. But how? Today, we're going to pull back the curtain on the magic of wireless networks.
It's a great question, isn't it? I mean, really think about it. You're in a busy coffee shop or an office, and there are maybe hundreds of devices all trying to talk at the same time, using the exact same airspace. How does your phone's data not just smash into someone else's laptop data? Well, that's the puzzle we're going to solve.
So we'll start with something we all use every single day, our home Wi-Fi. Because the first and maybe the most important job of any network is controlling who gets in and who stays out. It needs a gatekeeper.
That gatekeeper? It operates at what's called the MAC layer. And yeah, the analogy on this slide is just perfect. Think of it like a bouncer at some exclusive club. Its job is to manage the chaos at the door, make sure only the right people get inside, and ensure that whatever happens in the club stays in the club.
So this digital bouncer has three main gigs. First up, authentication. It's basically checking your device's ID to make sure you're on the guest list. Then you've got encryption. Once you're inside, it makes sure all your conversations are in a secret code so nobody can eavesdrop. And finally, access control. It decides which parts of the club you can go to, managing who gets to send information and who gets to receive it.
And this is where it all clicks into place for you. Every single time you type in a Wi-Fi password, you're actually interacting with these security protocols, like WPA2. That password is what kicks off the whole authentication handshake, proving to the bouncer that, yep, you're allowed in. So this isn't just some abstract theory, right? It's the absolute bedrock of your everyday digital security. Okay, so a router acting as a central bouncer, that makes a lot of sense. But what happens when you don't have one? Imagine a disaster zone after an earthquake, a military team in the field, or even a whole highway full of smart cars. How do they all connect? Well, they form what's called an ad hoc network. And the keywords here you gotta remember are decentralized and self-organizing. These networks literally build themselves on the fly, with no central boss. Every single device can be both a phone and a switchboard, talking directly to its neighbors. And hey, this isn't some far-off sci-fi stuff. It's being designed for our roads right now. In what's called a vehicular ad hoc network, or a VANET, your car could literally talk to the car in front of it, warning it that you're slamming on the brakes way before the driver could even see your brake lights. This is the kind of instant, decentralized communication that can make self-driving cars way safer. So what makes these networks so powerful is how darn flexible they are. This dynamic topology just means devices are constantly moving, joining, and leaving the network, and the whole system just adapts. And with multi-hop communication, a message can leapfrog from one device to another to cross a huge distance, kind of like a digital bucket brigade. And if a device drops out, no big deal. The network just finds a new path. It literally heals itself.
All right, that self-healing thing, it brings up a huge question. If there's no central router playing traffic cop, and the map of the network is always changing, how in the world does a little packet of data find its way to its destination? How does it get its own personal GPS?
There are basically two main game plans. Proactive routing is like having a complete, constantly updated map of the entire city with you at all times. You always know the best route instantly, but keeping that map fresh takes a ton of effort. Then there's reactive routing. This is more like firing up your GPS. You only ask for directions when you actually need to go somewhere. It might take a second to find the route at first, but you're not wasting all that energy mapping places you'll never go. Reactive routing is perfect for those constantly changing car networks we just talked about. So how does that on-demand GPS actually work? Well, it's a really cool, simple process. The source device basically yells out a route request to all of its neighbors. They pass the message on, kind of like a relay race, and each one leaves a little virtual breadcrumb saying, hey, the message came through me. When the destination finally gets the message, it just sends a route reply that follows that breadcrumb trail all the way back. And just like that, boom, a path is created. So we've got secure networks. We've got these incredible self-building, self-healing networks that find their own way. But are they any good? How do we actually grade them? Let's take a look at the network's report card. And here's the thing you have to remember. It's not just about that big speed number they print on the box. Real-world performance is a balance of a few key things that decide if a network feels fast and reliable or slow and just frustrating. First up is throughput. And honestly, this is the speed metric that really matters. It's not the theoretical maximum speed, it's the amount of useful data that actually successfully makes it to the other end. It's the real-world rubber meets the road speed.
This slide gives us a perfect, simple example. Let's say you're sending a 5 megabyte file, and it takes 10 seconds to arrive, fully intact. You just divide the size by the time, and bam! Your actual effective throughput is 500 kilobits per second. Simple as that.
Next is latency, or what pretty much everyone just calls delay or lag. This is the travel time for a single little packet of data. For just browsing a website, a little bit of latency, no big deal. But for a video call or an online game, oh man, even tiny delays can make the whole thing just fall apart. Lower is always better here. Now, what's really interesting here is that latency isn't just one thing. It's actually a total of several different delays all added up. As you can see in the calculation, you've got the time to get the data onto the wire, the time for it to physically travel, and the processing time at each little stop. All those milliseconds add up to the final number you experience as lag.
And finally, we've got packet loss. Sometimes, for whatever reason, data packets just get lost. They hit some interference, a connection gets too crowded, and poof, they vanish. You know that moment your video call freezes for a second, or the audio just drops out? Yep, that's probably packet loss right there.
And measuring it is pretty simple, actually. If you send out 10,000 packets and 200 of them just never show up, you have a 2% packet loss rate. For most things you do, you want this number to be as close to 0 as humanly possible.
So, when you step back and look at the whole picture, from securing a simple connection to building these self-healing networks and checking their vital signs, it's an incredible amount of complexity that just works. But as we barrel towards a future of smart cities, autonomous cars, and this massive Internet of Things, the big question is changing. It's not just about being fast anymore. It's about being smart, adaptive, resilient. So, are our networks really ready for what's coming next?